Hello there, and welcome to the Orbiting Truths channel. Tonight, we're turning our attention away from Earth and gently outward into deep space. Not the kind filled with explosions or flashing stars, but the quiet space between them. The long, dark regions where time stretches, motion slows, and ancient fragments drift unseen. This is the story of interstellar space. A place that is not empty, but thin. A place where objects move for millions of years without ever touching a star. As you listen, you don't need to remember anything. There's nothing to solve or understand. Just let the ideas pass by, like distant starlight through a window. If you enjoy these slow journeys through real science, you're welcome to like or subscribe. It helps others find their way here too. But for now, all you need to do is rest. Let your breathing slow, let your shoulders soften, and allow your thoughts to drift as we begin. Most planetary systems are not tidy places. When stars form, they are surrounded by disks of gas, ice, and dust. From this material, planets slowly assemble. But not everything becomes a planet. According to modern planetary formation models supported by NASA and ESA, a typical star system ejects enormous amounts of leftover material over its lifetime. On average, astronomers estimate that a single star may cast off around 10 quadrillion small bodies. Fragments of ice and rock, too small or too scattered to settle into stable orbits. These objects are flung outward by gravitational encounters, often involving giant planets. Once ejected, they no longer belong to any star. They drift. Over time, these fragments spread out into overlapping streams that wind through the Milky Way like invisible ribbons. Each stream slowly stretches, distorted by passing stars, by galactic tides, and by the slow rotation of the galaxy itself. By the time one of these relics reaches our solar system, its original path has been completely scrambled. Billions of years of motion erase its past. Interstellar space remains profoundly empty. Even with so many fragments, the density is incredibly low. Estimates suggest there may be far less than one large interstellar object per cubic astronomical unit. That means enormous distances between travelers. Far from any star, these objects grow cold. Extremely cold. Without sunlight, their surfaces darken. Cosmic rays strike them for millions of years. Slow chemical reactions alter their outer layers. Micrometeoroids chip away at them grain by grain. Over time, they become weathered not by wind or water, but by space itself. Some scientists believe these interstellar relics can sometimes act as seeds. If one passes through a young star system, dust and gas may collect around it, a foreign core helping local material grow. In that way, planetary systems may share matter across the galaxy. Each interstellar object carries what astronomers call a home velocity, a subtle memory of the motion of its parent star around the Milky Way. And when such an object enters our solar system on a fast, open path that no planet here could create, we know it was born elsewhere. Interstellar space is not still. Even in its emptiness, motion dominates. Every star in the Milky Way follows a path around the galactic center. Some move slightly faster, some slightly slower. Some tilt above or below the galactic plane. When a planetary system ejects debris, those fragments inherit that motion. They leave their birth systems already moving, carrying a velocity that reflects where they came from and how their parent star traveled through the galaxy. Once released, these fragments no longer orbit anything in particular. They become free travelers. Over millions of years, their paths stretch and twist. Passing stars tug at them faintly. The galaxy's gravity slowly reshapes their routes. This creates vast, overlapping streams of debris, too diffuse to see but very real. Astronomers know these streams must exist because planetary formation is messy. Computer simulations show that giant planets, especially those that migrate inward or outward, can eject enormous numbers of smaller bodies. Jupiter alone is capable of flinging objects completely out of the solar system during close encounters. Scale that up across hundreds of billions of stars, and interstellar space becomes a slow river of fragments. Yet, detecting any one of them is extremely difficult. They do not glow. They do not reflect much light. And most never come close to any star again. To be seen, an interstellar object must pass near the Sun, at just the right angle, at just the right time. And even then, it may only be visible for weeks. This is why astronomers look for motion, not appearance. A typical asteroid or comet follows an elliptical orbit. It is bound to the Sun. It returns again and again. An interstellar object does not. Its path is hyperbolic. That word simply means its orbit is open. It comes in once, and then it leaves forever. Mathematically, this shows up as an orbital eccentricity greater than 1. Anything above 1 cannot be held by the Sun's gravity. That is the first unmistakable signature. The second is speed. Objects native to the solar system have a limited range of velocities. They move according to long-established gravitational relationships. An interstellar object arrives too fast. Its excess velocity cannot be explained by any interaction with planets here. No planet could have accelerated it that much. That extra speed had to come from elsewhere. Astronomers also look at direction. Most solar system objects orbit roughly in the same plane, the plane of the planets. Interstellar objects can arrive from almost anywhere, above the plane, below it, or even moving backward relative to planetary motion. That randomness is another clue. Once an object is identified as hyperbolic, astronomers trace its path backward, not to find a specific home star, which is usually impossible, but to see how its motion compares to nearby stars. Many interstellar visitors move at speeds similar to the local standard of rest, the average motion of stars in our neighborhood of the galaxy. That suggests they were drifting quietly, not launched in some recent violent event. They may have been traveling for hundreds of millions of years. During that time, they would have cooled almost to absolute darkness. Far from stars, surface temperatures drop to just a few degrees above absolute zero. Ices harden, chemistry slows, radiation accumulates, cosmic rays alter surface molecules, changing colors and textures. Over long spans, the outer layers become chemically processed in ways rarely seen in solar system objects. This makes interstellar objects valuable. They are not just visitors, they are records. Each one preserves conditions from another planetary system, locked in ice and stone. And when one briefly enters sunlight, we get a rare chance to read that record. When Oumuamua was first detected, it was already leaving. That detail matters. Most solar system objects are discovered on their way in, brightening as they approach the sun. Oumuamua was found after perihelion, already fading, already retreating. That meant astronomers had limited time. Every observation mattered. As telescopes tracked its brightness, something unusual appeared. Its light curve varied dramatically, much more than expected. This meant one of two things. Either the object was extremely elongated, or it was very flat, or possibly both. Early models suggested a cigar-like shape, perhaps 10 times longer than it was wide. Later models favored a pancake-like geometry, thin and broad. Either way, it was unlike any asteroid or comet previously observed. As Oumuamua rotated, its brightness rose and fell smoothly, suggesting a solid body rather than a loose rubble pile. The rotation itself was strange. It was not spinning neatly around a single axis. It was tumbling. This type of motion, called non-principal axis rotation, often results from a past collision or an uneven force acting on the object. In the solar system, tumbling objects usually settle into stable rotation over time. But Oumuamua had been traveling through interstellar space for millions of years. There was no obvious reason for it to still be tumbling. Then came the next surprise. As astronomers refined its trajectory, they noticed a slight deviation. Not enough to suggest propulsion, not enough to indicate thrust, but enough to show that gravity alone could not explain its motion. Something was pushing it gently. For comets, this kind of non-gravitational acceleration usually comes from outgassing. As ice warms, gas escapes, producing a small but measurable force. But Oumuamua showed no visible coma, no tail, no obvious jets. That silence confused researchers. How could something be outgassing without looking like a comet? One explanation gained traction: hydrogen. Hydrogen ice is extremely volatile. When warmed, it sublimates directly into gas without producing dust. No dust means no visible coma. If Oumuamua contained frozen hydrogen, it could outgas invisibly, producing the observed acceleration. But hydrogen ice is fragile. Could it survive millions of years in interstellar space? Another idea emerged: nitrogen ice. Pluto and Triton have nitrogen-rich surfaces. A fragment chipped from a nitrogen ice world could behave the way Oumuamua did. Nitrogen sublimates cleanly. It could explain the acceleration and the lack of dust. Models showed that a nitrogen-rich fragment would thin and flatten over time, naturally producing a pancake-like shape. Still, uncertainties remain. Astronomers did not have enough data to settle the question fully. Oumuamua faded too quickly. It left too fast. What it did not do is equally important. It did not maneuver. It did not change course intentionally. It did not transmit signals. Its motion followed physics, quietly, predictably. It behaved like matter, not like machinery. And that matters. Science advances by restraint, by following evidence, not imagination. Oumuamua was strange, but not magical. It was unfamiliar, but explainable. Its value lies not in mystery, but in what it confirmed. That interstellar space is populated. That material moves between stars. That planetary systems share debris. After its brief visit, Oumuamua passed beyond the reach of telescopes. It is now fading again, returning to darkness. It will never come back. But its passage changed astronomy. For the first time, humans had directly observed material from another star system passing through their own. Not as a theory, not as a simulation, as a real object, moving through real space. And that realization opened the door for what came next. 2 years after Oumuamua, astronomers were ready. Surveys had improved, algorithms had sharpened. When 2I/Borisov appeared, it did not slip by unnoticed. This time, the visitor announced itself clearly. Unlike Oumuamua, Borisov looked like a comet, a fuzzy coma, a developing tail, active outgassing. From the start, its hyperbolic orbit marked it as interstellar. Its eccentricity was far greater than 1. Its speed could not be explained locally. But composition made it special. Spectroscopy revealed large amounts of carbon monoxide, much more than typical solar system comets. Carbon monoxide sublimits at extremely low temperatures. This suggested that Borisov formed far from its parent star, in a very cold environment, possibly beyond the equivalent of our Kuiper belt. Its nucleus was modest in size, likely between half a kilometer and 2 kilometers across, small but intact. As it approached the Sun, Borisov behaved as comets usually do. It brightened, its coma expanded, jets formed. This familiarity was important. It showed that alien planetary systems can produce comets very much like our own. But there were differences. The dust grains in Borisov's coma were unusually fine. Polarimetric measurements showed patterns similar to Comet Hale-Bopp, one of the most pristine comets ever observed. This suggested Borisov had been preserved well, protected from repeated heating cycles. It had likely never passed close to a star before. As it warmed, Borisov experienced outbursts. Fragments broke off, activity fluctuated. By the time it left the inner solar system, it had lost material, leaving pieces behind. Those fragments will remain here, mixing quietly with native debris. Tiny bits of another star system now orbit the Sun. Unlike Oumuamua, Borisov gave astronomers time. They observed it across months, across wavelengths, across instruments, and what they learned was profound. Interstellar comets are not rare. They are simply hard to see. Their chemistry overlaps with ours, but it is not identical. The galaxy appears to reuse ingredients, but in different proportions. Borisov was a reminder. Alien does not mean unfamiliar. Sometimes it means familiar, with subtle differences. And those differences carry history. By the time the third interstellar visitor arrived, astronomers were no longer surprised by the idea, but they were still surprised by the details. In July of 2025, survey telescopes operated by the Atlas program flagged an object whose motion did not fit. It was moving too fast, too straight, too open. Orbital calculations quickly confirmed it. This was not a bound solar system object. This was 3I/Atlas, the third confirmed interstellar traveler. Its trajectory was extreme. More extreme than Oumuamua, more extreme than Borisov. Its hyperbolic excess velocity was about 58 kilometers per second relative to the Sun. That speed could not be explained by any gravitational interaction here. No planet could have thrown it that hard. This object arrived already energized, already moving fast, already free. Its incoming direction pointed towards Sagittarius, near the dense star fields of the Milky Way's inner regions. That does not mean it came directly from the galactic center. Stars move. The galaxy rotates. But the direction hinted at an origin in crowded stellar neighborhoods, where gravitational encounters are common and ejections are frequent. Its orbit was tilted dramatically, nearly 175 degrees relative to the planetary plane. It moved retrograde, cutting across the solar system almost backward compared to the planets. This alone ruled out any local origin. Then came another difference. 3I/Atlas showed a coma. Faint, but real. This was not a bare shard. It was a comet. Polarimetric measurements revealed unusual negative polarization, a property tied to dust grain structure. Its dust reflected light in ways similar to distant trans-Neptunian objects, yet not identical. Spectroscopy revealed volatiles, carbon dioxide, carbon monoxide, traces of metals like nickel. This chemistry pointed to formation in cold regions, but with conditions different from our own outer solar system. Estimates of its size were striking. Its nucleus appeared to be between 5 and 10 kilometers across. That made it significantly larger than both Oumuamua and Borisov. This was not a fragment. It was a survivor. During its passage, 3I/Atlas traveled within the orbit of Jupiter, hundreds of millions of kilometers from Earth, yet bright enough to study. Its perihelion occurred around 1.4 astronomical units from the Sun. It never came dangerously close. Most interstellar objects do not. They pass through quietly, skimming the inner system, never interacting with planets at all. Models tracing its motion backward suggested something remarkable. 3I/Atlas may have originated in the Milky Way's thick disk. If so, it could be older than our solar system, possibly 7 billion years old. That means this object may have been wandering the galaxy before the Sun ignited, before Earth formed, before oceans existed, before life began here. It carried chemistry frozen in time, not preserved by intention, but by distance. As it receded in early 2026, its coma faded. The Sun's warmth fell behind it. Like the others, 3I/Atlas did not slow, did not turn back. It resumed its long journey through interstellar darkness. One star briefly illuminated it. Then it was gone. Individually, Oumuamua, Borisov, and Atlas are curiosities. Together, they are evidence. They show that interstellar space is not empty. It is sparse, yes, but not vacant. Planetary systems eject material efficiently. Gravitational encounters, giant planet migrations, stellar flybys. All of these processes scatter debris. Models suggest a typical star may eject around 10 to the 16 small bodies over its lifetime. Most drift unseen. Most never approach another star closely. But some do. And when they do, their motion tells a story. Hyperbolic orbits are signatures of exile. Excess velocity is proof of ejection. These objects were not gently released. They were thrown. Their home velocities preserve the motion of their parent systems around the galaxy. Each one arrives with memory embedded in speed. Their compositions tell another story: carbon monoxide abundance, nitrogen ice possibilities, metal-bearing dust. These reveal diversity in planetary chemistry. The same basic ingredients appear again and again, but the ratios change. Temperature histories differ. Disk structures vary. Planet formation is not a single recipe. It is a family of outcomes. The fact that Borisov looked like a classic comet while Oumuamua did not shows that interstellar objects come in many forms. Some are icy and active. Some are dry and quiet. Some are large and luminous. Some are small and faint. What unites them is origin. None were born here. None gained their energy here. They are not messages. They are not probes. They are witnesses. Fragments left over from the construction of other worlds. Their value lies in what they record: ejection violence, disk chemistry, galactic dynamics. They let us study other planetary systems without leaving home. Each detection sharpens our understanding. Each new orbit improves population estimates. Each spectrum adds detail to alien chemistry. The rarity of detection does not imply rarity of objects. It reflects survey limits. As telescopes improve, detections will increase. Future observatories will find dozens, then hundreds. Each one will add a data point to a growing map of galactic debris flows. We live inside that flow. Our solar system is not isolated. It is embedded in a slow river of ancient fragments drifting between stars. Imagine the space between stars, not as emptiness, but as silence, cold, sparse, dim. Objects move there without friction, without sound. They drift for millions of years unchanged. Occasionally, a star lights them briefly, then they fade again. Oumuamua has already left the planetary region of the Sun. Borisov follows behind it. Atlas will soon be farther still. All three now move outward into darkness. Their paths diverge, their destinations unknown. They will not meet again. They will not be remembered except in data. But their passage changed how humans see the galaxy. Not as a collection of isolated systems, but as a connected environment. Material moves. Fragments travel. Planet formation is not local, it is galactic. As you rest, let that idea soften. Imagine a wide, dark volume threaded with slow motion. Tiny relics drifting, no urgency, no intention, just motion. Stars glow briefly as objects pass. Then the dark returns. Your breathing slows. Thoughts loosen. The galaxy continues without needing attention. And somewhere, far beyond sight, another fragment begins a journey that may one day cross another star's light.